Chapter 8b. In this section, we're going to study many electron atoms, starting with helium atom. Here shows the Schrödinger equation for the hydrogen atom. We have kinetic energy operator for the two electrons, the potential energy operator due to the attraction force of the nucleus and the electron 1, potential energy operator due to the attraction force of electron 2 with the nucleus, and the potential energy operator due to the repulsion force between the two electrons. It is because of this repulsion force that make this Schrödinger equation difficult to solve analytically, and therefore approximations must be made, which will be explained in the next few slides. The key approximation is called orbital approximation. Under this approximation, each electron occupies its own hydrogenic orbital. We ignore electron correlation, assume any one electron sees only the spatial averaged position of all other electrons. The many-electron wave function is therefore a product of one-electron orbitals. In 1921, Otto Stern and SternGerlach did an experiment to confirm the quantization of angular momentum of atoms by shorting a beam of silver atom through an inhomogeneous magnetic field. Their idea is each atom possesses a certain electronic angular momentum, which behaves like a small magnet bar. So according to hydrogen atom, the angular momentum should be quantized, and therefore you should see only certain orientation or discrete orientation and a number of sharp bands as shown here. Otherwise, according to classical expectation, then the magnet should have random orientation, which leads to a broad band. Now, their experiment was successful in that they only see a few sharp bands. Okay, that seems they proved angular momentum of silver atom is quantized. Okay, however, they only see two bands. Okay, only see two. And according to hydrogen atom, the angular momentum quantum number can be 0, 1, 2, 3. These are the allowed quantum numbers, and each quantum number L, you may have different orientation. For example, when L equals 0, M can only be 0. That means you only have one orientation. When L equals 1, then you can have a 0, positive, negative 1 for M. So in other words, you may have 3 orientation. So you should see 3 bands. And so in general, you should see 2L plus 1. These are the quantized angular momentum orientation that you should see. However, their experiment only see two bands. So if this equals 2, then L has to be one half. And that's not in the list of allowed angular momentum, orbital angular momentum quantum number. And so the suggestion of this experiment is that there's another type of angular momentum, not due to the orbital angular momentum, but due to the rotation of electron, and we call this electron spin quantum angular momentum. And we're going to talk about this more in the next slide. The SternGerlach experiment indicates that electron has intrinsic spin, and the spin quantum number can only be 1/2. The magnitude of spin angular momentum can be calculated by h bar times square root the quantum number spin times s plus 1. Now this is similar to the equation to calculate the magnitude of orbital angular momentum in hydrogen atom, which is H bar times L plus 1. And in hydrogen atom, the angular momentum, orbital angular momentum, even though we don't know the orientation, we know the z component, which is quantum number m times h bar. Similar, in this case, the z component of the spin quantum number, angular momentum, is also defined, can only have two values. Here is positive 2.5, negative 0.5. This can be represented by the two cones. This cone represents the spin with z component negative 0.5, and this one is the spin with z component positive 0.5. Again, the orientation is uncertain, as you can see here. It can be anywhere along this cone, but the z component is defined positive 0.5. Here is negative 0.5. Okay. In fact, this can be represented by alpha state, and this is defined by beta state. So now the total hydrogen wave function, you need 4 quantum numbers. And so this is one s orbital, which is n equals 1, l equals 0, m equals 0, and here the spin quantum number ms is a positive 0.5, and so it's alpha state. So this is the spatial wave function that you already see when we talk about the hydrogen atom, but now you multiply by a spin wave function alpha. Similarly, the beta state, well, the ms is negative 0.5, is the spatial part wave function of 1s orbital times the beta spin wave function. Spin is an important property not only to electron but also to many other elementary particles. For example, protons, neutrons, they all have half-integer spins. They are called fermions. Photon, which has a spin 1, is a boson. Now, fermions obey Pauli exclusion principle, and we're going to explain the next few slides. Let's construct the wave function for helium atom. Helium atom has 2 electrons. Each electron has its own wave function, so the total wave function is a product of the 2 individual wave functions. You may write it as psi r1, psi r2, means electron 1, electron 2, different wave function, or psi 1, psi 2 product. Okay. Now electrons also has a spin, 2 spin state, alpha and beta. So the combination of 2 electrons can be both in alpha state. So this means 1, 2 electrons both in alpha state or both in beta state. But what about 1 in alpha, 1 in beta? Can we write as this? Alpha 1 means electron 1 in alpha, electron 2 in beta, or electron 2 in alpha, electron 1 in beta. There's a problem to write like this way. Electrons are indistinguishable. So if we write it like this, that indicates we can distinguish electron 1 from electron 2, and that's not allowed. And therefore, we need to modify this. And one possible way to write is alpha 1 beta 2 plus beta 1 alpha 2. Okay, in this way, we say electron 1, electron 2, they are in different state, but they are not distinguishable. Now, we can also write negative, okay, alpha 1 beta 2 minus beta 1 alpha 2. The reason is the wave function itself does not have meaning. It's the squared tells you the probability. So when you square it, negative sign becomes positive. So then these two are both possible. So the first one actually can be represented by this diagram, which means 1 electron in the alpha state, 1 in the beta state, and because they have a positive sign, so they do not cancel each other. They are parallel spin. The other one you can represent like this: two cones. One is in the beta state, one is in the alpha state, that always in the opposite direction. They cancel each other, so it is a paired spin. So in chemistry, we may write as up and down in the paired state. Okay, so now to write the total wave function, we need to include the spatial wave function and the spin wave function. You have both alpha state, both beta state, or one in alpha, one in beta. So 4 of them. So here are the 4 possible wave functions. The spatial wave function are always the same, the product of the 2 individual wave functions, and then spin both alpha, both beta, 1 alpha, 1 beta, 1 alpha, 1 beta. So you have 4 ways to write the total wave function for helium atom. But which one is the correct one? Okay, we'll see in the next slide. Let's now introduce Pauli principle, which says that when the labels of any 2 identical fermions are exchanged, so in this case, we say the electrons, the labels are exchanged, then the total wave function must change sign. Okay, so here are 3 of the 4 wave functions we constructed for helium atom. Both electrons are beta spin, alpha spin, or 1 beta, 1 alpha. Okay, so let's try the first one. Let's exchange the label. 1 becomes 2, and 2 becomes 1. So psi 2, psi 1, beta 2, beta 1. And you can see after change the label, the product is the same as the original product. So it does not change sign of the wave function, and therefore this is against Pauli principle. Now similarly, when you change the second label wave function, 1 to 2, 2 to 1, 1 to 2, 2 to 1, and the wave function does not change sign. So it's against the Pauli principle, and the same is the third one. The only wave function left is this one with a negative sign here. Now if you change the label, exchange the labels 1 to 2, 2 to 1, 1 to 2, 2 to 1, 1 to 2, 2 to 1, and then you will see the product of the whole wave function is negative of this original wave function, and therefore it does change sign, and this is the only possible wave function that obeys Pauli principle, that when you exchange the labels, the wave function changes sign. Okay. Now remember, this wave function can be represented by 2 cones. All right. So 1 spin is in the alpha state, 1 in the beta state, and they also always in the opposite direction, and so this is called paired states. And if we have more than 2 electrons, it is more convenient to write wave function instead of using this form. We can write as determinate form. So this is a more concise form to write wave functions that obeys Pauli principle. Okay, Pauli principle is this one. Now, one important property for this determinate is that when the 2 rows are the same, then this wave function is 0. And when 2 rows are the same, that actually indicates the 2 electrons have the same spin. Okay, both are alpha state, or both are in the beta state. Now, for helium atom, 2 electrons, 1 and 2 electrons, are already in the same orbital. For example, 1s orbital. Okay, that means they already have the same quantum number n, quantum number L, quantum number M, same quantum numbers. Now, if this is 0, when the two rows are the same, that means that they also have the quantum number spin the same. So in other words, 4 quantum numbers are all the same for the 2 electrons. Then the wave function does not exist. So the conclusion is no 2 electrons in an atom can have the same value of all 4 quantum numbers, N, L, M, S. Okay, so if you have 2 electrons in an atom, they cannot have exactly same quantum number N, L, M, S. One must be different. All right, so we'll talk more in the next slide. In the last slide, we showed that Pauli principle indicates that no 2 electrons in an atom can have exactly 4 quantum numbers N, L, M, S. All right. So the question now is, how many electrons can one orbital hold? Okay. So let's say here is orbital. Can this orbital hold 3 electrons? Okay. Now remember, one orbital means N, L, M are already the same. So if we have, let's say, 3 electrons, all right, they have the same N, L, M. So now if one is in alpha state, the second one must be in the beta state because they must have different 4 quantum numbers. All right. So what about the third one? If third one is up, then these two has the same exactly quantum state. Or if the third one is down, then these two will be in the same quantum state. And therefore, that indicates one orbital can only hold 2 electrons. Okay, the maximum occupancy is 2 electrons. Also, if you have 2 electrons in the orbital, one must be spin up, one must be spin down. So their spin must be paired. This can be represented by this 2 cones with 2 vectors lie at an indeterminate position. But if one lies on one cone, the other must be in the opposite direction. The total spin angular momentum is 0. They cancel each other. We just introduced the Pauli exclusion principle, which says that one orbital can only hold maximum 2 electrons, and they must be in the opposite spin. What happens if we have more than one orbital that have the same energy? And this is addressed by Hund's rule, which says electrons occupy different orbitals of a given subshell before doubling occupying any one of them. Let's have an example. For nitrogen, the electronic configuration is 2s to 2p, so you have 3 electrons. Now the 2px, 2py, 2pz are in the same subshell, same energy, and according to Hund's rule, the 3 electrons must go to different orbitals instead of doubling into one orbital. But what about the spin? So you have 3 orbitals, each of them has 1 electron. Are they in opposite spin or different, same spin? And this is addressed by the second Hund's rule, which says an atom in a ground state adopts a configuration with the greatest number of unpaired spins. And therefore, that means these 3 electrons, they must be in the same spin state, so they are unpaired. Okay, and therefore we can draw like this one. So in this case, all the spins are in alpha state. In order to calculate the approximate wave function, we use variation theorem. Suppose psi naught is the true wave function, and the associated energy is E naught. But we cannot solve this Schrödinger equation analytically. So what can we do? If we have a approximate wave function, the variation theorem says the energy associated with this approximate wave function is always greater or equal to the true energy. And therefore, if we can somehow minimize the energy of this wave function, then we can approach the true wave function and the true energy. And therefore, to find the good approximate wave function, we parameterize the trial wave function, find the optimal values for the parameters by minimize the energy with respect to each parameter. One of the most commonly used calculation is called Hartree Model. So the Schrödinger equation for the total wave function can be separated into many one-electron Schrödinger equations, such as this. Now we are going to skip all these details to the next. So again, this is the procedure to use Hartree-Fock self-consistent method. And we'll skip all the details, but one important parameter that will be optimized in this calculation is called effective nuclear charge, and we'll explain in the next slide. Suppose we have an atom with positive nuclear charge Z plus in the nucleus, and let's say we have two electrons. One is closer to the nucleus, one is further away. The second electron feels nuclear charge actually less than Z because the Z is partially cancelled by the first electron. And we say electrons are shielded from the 4 nuclear charge by other electrons. And the effective nuclear charge is therefore less than the 4 charge of the nucleus. And you can use the 4 charge minus a shielding constant. The shielding constant depends on the wave function, the quantum numbers of the other electrons. Here shows the calculate the effective nuclear charge for helium and carbon. In helium atom, we have 2 nuclear charges, and 2 electrons in one s orbital both feel effective nuclear charge 1.6875, which is less than 2. That indicates that these 2 electrons have shielding effects on each other, even though they are in the same subshell. When we go to carbon, which has 6 nuclear charges, the 2 electrons in the first 1s orbital feel effective nuclear charge 5.6, which is slightly less than 6. But for the 2 electrons in 2s orbital, the effective nuclear charges are greatly reduced to 3.2. So that indicates that the core electrons, in this case is 2s orbital, are more effective in shielding auto electrons than the electrons in the same shell. For the electrons in the 2s2p orbital, the effective nuclear charge also decreased from 3.2 to 3.1. So the s electron has a greater penetration through inner shells than a p electrons, because s orbital is more likely to be found closer to the nucleus than the p orbital. And we'll see more in the next slide. Here shows more effective nuclear charges. For hydrogen, there's only 1 electron, so the effective nuclear charge is the same as the nuclear charge. Lithium has 3 electrons, so there's 3 nuclear charges, but the effective nuclear charge for the outermost electron, or the valence electron, is only 1.28. Beryllium effective nuclear charge for the valence electron increased to 1.91. In fact, the effective nuclear charges for the valence electrons increase from left to right. This is because the nuclear charge increased from left to right, although the valence electrons also increase from left to right. those electrons are all in the same shell, and the shielding effect is less effective, and that causes the effective nuclear charge increase. And one of the consequences is the radius decrease when we go from left to right. Here shows the radial distribution functions for 3s, 3d, 3p orbitals. As you can see, the subsidiary maximum in 3s orbital is closer to the nucleus than 3p, which is closer than 3d. So that explains why s electron has a greater penetration through inner shell than p orbital and d orbitals. And the consequence of this is that the electrons in these orbitals have different energies. Within a shell of principal quantum number n, the s orbital has lower energy than p orbital, which is lower than d orbital. And this is in contrast to hydrogen atom, where all these orbitals has the same energy. Here shows the orbitals arranged according to the energy. With the Pauli exclusion principle and Hund's rule, we now can place the electrons from low energy orbitals to high energy orbitals. This is called the build-up principle or alphabet principle. We'll see some examples in the next 2 slides. This shows the electronic configurations for the first 3 rows for main group elements. In hydrogen, there's only 1 electron which goes to 1s orbital. And then for helium, 2 electrons both goes to 1s orbital. So up to this point, the first shell is 4. And then in lithium, because the electrons already filled the first row, we can use bracket helium to represent the electrons already filled the first shell, and the actual electron goes to the second shell, 2s electron. For beryllium, 2s, you have 2 electrons. And for boron, an actual electron goes to the p orbital, 2p1, and then 2p2 until 2p6 in neon. And so up to this point, the second shell is 4. Okay, so then go to sodium, and we use bracket neon, means the electrons already filled all the orbitals until neon. And then the actual electron goes to the third shell, 3s1 electron. And then magnesium, 2 electron in 3s orbital, and aluminum, the electron goes to the p orbital until 3p6 for argon. So up to this point, the third shell is 4, except the 3d orbital, which we're going to see in the next slide for transition metals. Here shows the electronic configurations for the 4th row atoms. As we saw in the last slide, argon has the electronic configuration up to 3s2, 3p6. So the next electron for potassium you would expect to go to 3d orbital. Instead, it goes to 4s orbital, and the reason is due to the shielding effect and penetration effect, and so that brings the 4s orbital down in energy. Similarly, for calcium, the 2 electrons goes to 4s orbital. Now for scandium to zinc, all these orbitals, the d orbital, 3d orbital, is always lower in energy than 4s by calculation. And so from calculation, you would expect for scandium, the electronic configuration should be 3d3. All right, so the electrons in 2s orbital should also go to the d orbital, because d orbital is lower in energy. However, instead, it keeps 2 electrons in the 4s orbital, but only 1 electron goes to the d orbital. And the reason is, even though 3d orbital is lower in energy, the average distance is less, and therefore when electrons are placed in the 3d orbital, it becomes more repulsive. The repulsive force becomes more severe, and therefore instead it keeps the 2 electrons in the 4s orbital. In fact, from scandium to zinc, most atoms keep 2 electrons in 4s orbital, but the extra electrons goes to 3d orbital. Now, 2 exceptions. One is chromium. And so look at the vanadium, 3 electrons in the 3d orbital. So the next electron you would expect to be 3d4. So 4s 2 3d4. Instead, it brings 1 electron from 4s to 3d, so becomes 4s1 3d5. Another exception is copper. So looking at nickel, the electronic configuration is 4s2 3d8. So you would expect copper should be 3d9. But instead, it brings electron from 4s to 3d, so it becomes 3d10 and 3d10 and 4s1. In both cases, copper and chromium, the atom try to achieve either half 4 or 4 in occupancy in d orbital, and this is favorable for the minimizing of energy of the atom. As we already explained, from left to right, effective nuclear charge increase, and this increase draws electrons closer to the nucleus, and therefore the atomic radii decrease from left to right. From top to bottom, atomic radii increase, even though the effective nuclear charge also increase. And this is because we are adding more shells to the atoms, because the principal quantum number increase. Similar to the atoms, the ionic radii also decrease from left to right and increase from top to bottom. Cations are usually smaller than their parent atoms, and anions are larger. The ionization energy is defined as the minimal energy necessary to remove an electron from a ManyElectron atom in a gas phase. The ionization energy increased from left to right in the periodic table, from lithium to neon, sodium to argon, potassium to krypton. And this is because from left to right, the effective nuclear charge increase and the atomic radii decrease, and therefore it takes more energy to remove an electron from the atom. The ionization energy decrease from top to bottom, from lithium to sodium to potassium, rubidium, cesium. And this is because from top to bottom, the atomic radii increase, and therefore it takes less energy to remove electron from the atom. Electron affinity is defined as the energy released when an electron attaches to a gas phase atom. It's a measure of the ability of an atom to attach to an electron. A positive number here indicates electron attachment is exothermic, and this is opposite to the convention that exothermic is negative. So chlorine, fluorine has very positive electron affinity, means they have high ability to attach to electrons. Oxygen, on the other hand, has a electron affinity 140, and the anion has negative 844, and this is due to the strong repulsion force of electrons on an anion. Here is the summary of periodicity. The atomic radii decrease from left to right across the period and increase down a group. The consequence is the ionization energy increase from left to right across the period and decrease down a group. The trend for electronegativity is the same as the ionization energy. Before we end this chapter, let's think about what happens when an electron is excited in helium atom. In the excited state, one electron in the 1s orbital, another electron goes to the 2s orbital. So what are the spin states of these two electrons? These two electrons can be paired, and that's described by the first diagram, where the two electrons, one is in alpha, one is in beta, and they are always in the opposite direction. And so the total spin is 0. There's no net spin. And this is called a singlet state, because there's only one way to achieve this spin state. So the wave function of this state is written as this one that you already see before. The two spin can be parallel. So if they are parallel, then non-zero spin, total spin, can be generated. And this can be achieved by 3 ways. One is both are alpha state, or both are beta state, or one alpha, one beta, but they are parallel. And in all cases, the total spin is 1. All right, and so this is called a triplet state, because we have 3 possible ways to generate the spin s equals 1. Okay, so these are the wave functions. Again, you have seen this before. And so for states arising from the same configuration, it turns out that the triplet term generally lies lower than the singlet state. In other words, triplet state has low energy than the singlet state. When an electron spins, it generates a magnetic field like a small magnet. So is the orbital angular momentum. The interaction of a spin magnetic moment with the magnetic field arising from the orbital angular momentum is called the spin orbital coupling. The relative orientation of the spin and the orbital magnetic moment cause different total angular momentum. For example, in diagrams A and B, both orbital angular momentum has orientation up, but the spin angular momentum can be up and can be down. So these cause different angular moment, total angular momentum. The total angular momentum of an electron is described by quantum number J and Mj. So in the first case, because the orbital angular momentum and spin angular momentum are in the same direction, so we add these two together. So L is the orbital angular momentum quantum number, and half is the spin angular momentum quantum number. Now, in the second case, they are in opposite direction, so L minus half. Okay, and so the energy is calculated by this equation, which you need to know the orbital angular momentum quantum number, the spin quantum number, and the J that we just described here. Okay, so we have a spin orbital coupling constant, the J constant, the orbital angular momentum quantum number, and the spin quantum number. So here is example. Identify the levels that may arise from the configuration of D1 and S1. So if we have electron in the d orbital, do we have spin orbital coupling? So for a d orbital, L, so L equals 2. All right. Now the spin can have the same orientation as the angular momentum, orbital angular momentum, or opposite. So you have two possible orientations. So J can be 2 plus half or minus half, and therefore we generate two levels, okay, two different angular momentum, and therefore two different energies. Okay, note that the J is calculated by a vector addition. Now what about s orbital? Okay, if you have electron in s orbital, the angular momentum, orbital angular momentum quantum number is 0. Okay, so now the energy is only due to the spin, and therefore here you only have one state, is half. Okay, so one state for electron in the s orbital. The emission spectrum from sodium vapor gives a yellow line at 589 nanometer. And if you look very closely, and this line actually is a doublet. Okay, the two lines are very close to each other. And let's explain why this happens. And this emissions line is due to the electronic transition from excited state 3p orbital to the ground state 3s orbital. At the ground state, when the electron in the s orbital, the angular momentum quantum number is 0. So the orbital angular momentum quantum number is 0, and therefore there's no spin orbital coupling. The energy coupling energy is 0. You only have one energy state. That's the ground state. Now in the excited state, electron in the p orbital, so the orbital angular momentum quantum number is 1. And the electron spin can be in the same orientation or opposite orientation. So you have two energy state. So J can be 1 plus half or minus half. And therefore, the two energies can be calculated. So here is coupling constant and J quantum number, and L quantum number, and S quantum number. And so you calculate two different energies. And these two different energy give you the difference 17 inverse centimeter, which is observed in the experiment.